vision, fundamentals, and application. This is the first time that this course is given, and that wouldn't be possible without this amazing team. On the instructor side, we have Assaf, Shai, and Merav, and on the TA team, we have Achiad, Ben, and Dror, Nir, and Shir. So actually, Assaf is the one who's gonna teach the first 3 classes. And today I just wanted to kind of like welcome you and still a couple of minutes to just introduce myself and also give my 2 cents on entering this field of deep learning and computer vision. So a bit about myself. I completed my PhD in Tel Aviv University in Israel under the supervision of Shai Avidan and Yael Moses. And then I moved to the US for a postdoc in MIT with Bill Freeman. And then I just moved across the street from MIT and joined Bill's research group at Google. And I've worked there as a research scientist until very recently. Actually, I'm still working at Google part-time as a staff research scientist. And I've joined the Weizmann Institute just a couple of months ago, and I'm starting to build my own group here, working at the intersection of computer vision, computer graphics, and deep learning. And when I did my PhD, this intersection looked something like this. You know, most of the works in computer vision didn't involve deep learning. Actually, you know, most of my PhD work was based on Gould old formation models, classical computer vision algorithms, and so on. But today, everything has changed, and deep learning has completely taken over the field first of computer vision, and now also graphics. And now, you know, there is no work in CVPR or any of the top tier conferences that doesn't involve deep learning. It's very rare. And to be honest, it took me some time to get into deep learning and adopt these powerful tools. So in 2017, I was still like, I had to give talks using this slide. I had to warn people in advance, you know, I'm sorry guys, I'm not gonna talk about deep learning today. And I think one of the reasons was that it seems like these huge models are data hungry, they're not rigorous. I don't wanna throw away all the stuff that I learned about, you know, computer vision, signal processing and optimization, and it was quite scary. But of course, since then, you know, all my work since 2017, I think, kind of like involved deep learning, and it's a really powerful tool, and it's a very exciting time to be in this field. For you guys, the situation is so different because you are entering this field where, you know, the integration of deep learning tools and algorithm and methodologies is inseparable from computer vision. And I just want to give you a couple of advices about, you know, how to start the way I see it. So my first advice is actually, you know, don't leave out the fundamentals. I encourage you all to take classical courses in computer vision, in computer graphics, in signal processing. You know, computer vision is a very long-standing field, and classical method, they have such cleverness embedded into them. You know, we are keep, you know, running jokes on that, but you know, that there was a time where computer vision, people were smart. And there is a lot of, you know, great ideas there, like, you know, image representations, image pyramids, Laplacian pyramids, geometric representations, objective functions, handcrafted features, and so on. These are very valuable ideas and concepts that I encourage you all to adopt. And I actually think that we kind of like in the area now. We understand that it's not enough to throw data on these deep learning models. We want to integrate the fundamental concept that we learned into them. The first advice is, you know, strive to understand your model, be critical. Like a deep network is a function with millions or billions of parameters. It's very easy to kind of like only look at the end results and that's it. But I want to encourage you all to keep asking the question, what does the model learn? convince yourself that the model doesn't cheat, like it doesn't pick up those trivial signals, it doesn't overfit, understand the failure cases and the limitation of your models. These are very important things to notice. And related to this point, the reason that I entered the field of computer vision is that I love image data. It's a real signal in the real world, and it's all around us. So don't just lean on accuracies and training curves. Always look on your pixels, lab the pixels, look at your data in all times. And the last advice before I hand the talk to Assaf is, as I said, dream big. Now this is a very exciting time to be in this area of computer vision. Computer vision methodologies that are based on deep learning are all around us. We use them in every day, whether if we want to be creative and create those filters that we wear on our faces. In all industry products, computer vision is integrated into those products and helping the world, be creative, and the technology is really out there and working. So we will have a final project in this course. Assaf will talk about it, and this is an opportunity for you to dream big and be creative in this course. And without further ado, I'd like to hand the rest of this class to Assaf. Thank you all, and welcome.
Hey, great. So hi, nice to meet you, everyone. My name is Assaf, and in this class we have today, so we're going to just shortly discuss some of the logistics of the course, and then we're going to start with our first topic. So let me just briefly state that we are very much aware of all the online courses that exist, and we think they're great. We've all learned from many great resources. And when we were curating this course, we were definitely using what they had to offer. So misquoting Isaac Newton, we're saying that if we've seen farther, it is by standing on the shoulders of giants. So we learned a lot from the Stanford course, the famous one, the CS231N, and the deep learning book was also a big inspiration for us. However, there are many differences, and we have our own agenda. So, first of all, one thing that is very important for us is to start from the very basics, understanding the most simple ideas of deep learning and in computer vision. But we're also, it's also very important for us to go for the state of the art, for the most recent works, and be updated all the time. If we have to change things because things, new papers rise during this course, then we will update accordingly as we go. One small thing is that while this is a general introductory course, but we are slightly biased towards the research done here at the Weizmann Institute. So you will mostly feel it during the second half of this semester that we are injecting a little bit of the things done in the labs over here. It is our philosophy that the way we're going to teach is going to include a lot of intuition. It is important to grasp the ideas, not just do it practically be able to do stuff with neural networks on one side, and also not going just dealing with theory on the other side, but true understanding, grasping why things work the way they do. And the other thing is this is a hands-on course, so you're going to have hands-on homework. We're going to discuss the homework in a while, and and we encourage you to be able to implement and to practically be able to make things work, not just theoretically understand them. And the last thing we advocate is openness, and this is by many, this has many meanings. So first of all the course material, videos of the lectures, tutorials, homework, whatever, everything is going to be open to public, to whoever want to access this. And this also has other meanings. So everything is going to be eye level. You can all feel free to ask questions, to approach. Your success is what we're interested in. We want you to understand the best you can and to enjoy and to eventually be able to practice deep learning in the best way. So please feel free to communicate with us. So just quickly, a few things about logistics. So everything is on the course website or the Piazza, so you can find whatever you need over there. So I'm not going to go through tons of details now. I'm just going to mention, so to those who are not updated, this is a 4 credit points course. We have 2 hours of lecture each week and 1 hour of tutorial. And just note that tutorials, they're not just recapping or anything like this. We teach new material at the tutorials. We're going to have 4 homework assignments and a final project. And please note that all communication will be done through the Piazza. It's the best way to send messages to everyone and to communicate, and your friends can answer sometimes questions if someone of us hasn't seen it yet, etc. I should say that if there is something personal then that you want to talk about, then feel free to email one of us, and then it will be private. So there are prerequisites at the Feinberg website, but we just want to mention the thing that we assume you know before we start. So we assume that you know basic calculus. So a rule of thumb is if you know what a gradient is, then you're probably okay. We also assume you know basic linear algebra, so vector spaces, eigendecomposition, all of this stuff. I'm sure all of you are good with this, and it's important. We also assume that you have written code before, most preferably is Python. But if you used any other language and you know how to manage well, so Python is pretty easy to learn, so you'll probably be okay. And we also like to assume that you bumped into machine learning. So you're not an expert, and maybe you've never done any course in machine learning, but you have been in some kind of relationship with this field. So one rule of thumb there is that if you just overheard someone saying the term overfitting, then it sounds okay, then you'll probably be fine. Regarding the homework, so we have this this whole philosophy about homework. It's going to be divided into each assignment, except the 2 first ones, which were kind of one assignment that gets splitted. But generally, all the assignments are going to be split into 3 parts. So we have the first part, which is the theory part. It's going to be just very small, solving 1 or 2 theoretical questions. This will be, you'll be using, you will send us your PDF of the solution. The second part is called from scratch. And in this part, you're going to use very basic programming. So you're not going to take advantage of deep learning tools. You're going to implement from scratch many of the methods and the algorithms that we're going to learn. And the reason we do this from scratch part is that the only way, as I see it at least, to really understand something and not to lie to yourself that you understand something is to implement it by yourself and get results. And then you know that every little detail that sometimes people fail to mention, you jumped over this, you jumped through this hoop, and you now understand this detail also. And lastly, of course, is the applied part, where you will take advantage of deep learning framework to be able to solve like the bigger problems. And of course, this is super important because this is what people who practice deep learning eventually actually do. And about the framework that we're going to use, so you may be aware that there are two main frameworks. It would be TensorFlow and PyTorch, and usually people are very into one of these frameworks. So you can see that COVID-19 brings people less apart than their favorite framework, and we're definitely going to pick a side in this conflict, and we're all about PyTorch. So this is what we're going to use, and also note that homework number 1 is online. Okay, so it's due in about 2 weeks. So look at the Piazza and go and start working it. So this is the idea for this slide I took from Justin Johnson, and this is to understand where we stand. So this course is going to be at the field of artificial intelligence, and within artificial intelligence there are many fields, and the simplest one that existed for many years was sort of rule-based AI, where you as a human you set this list of rules that determine how your algorithm is going to act. And I have much respect for it, because people who practice this, they need to understand what they're thinking, what is the process of decision making that they do, and they try to imitate it by algorithms. But in this field, there exists the field of machine learning. So machine learning is not about setting this list of rules. Machine learning is about setting an algorithm that actually produces this set of rules using data. So it's what we call data-driven approach. We use the data, and we finally get a set of rules that sometimes we can't even follow them because they're maybe too complicated for us. Another field which is very important for us is the field of computer vision, and it includes many approaches and many methods and many subfields. Many of them are classical, but there is a very big and respectful overlap between computer vision and machine learning. And within the machine learning field, there exists the deep learning field. Deep learning is the field of learning using artificial neural networks. We're going to discuss mostly in our next meeting, we're going to discuss what these things are. But this is a subfield of machine learning, and where we stand is exactly here. So we're going to use deep learning, which is a part of machine learning, for computer vision. And this is what this course is all about. And let me just super briefly show you cool things that deep learning can do. So in this work by Andrei Karpathy and Fei-Fei Li, it's from almost 6 years ago, you can see the challenge of image captioning. So for example, you can see this picture right here, and the algorithm is able to produce this sentence: black and white dog jumps over a bar. And you can see also the others, and this was already done 6 years ago. Here's another example. So this is object detection, and this is a challenge that people work on a lot. You can see how it works in real time. So this is also one of the things that deep learning has brought us to do. And here's something very recent. So this is in the field of generative models. So for example, what if you type this sentence right here: an armchair in the shape of an avocado, and then your algorithm that has never seen such a thing before just invents these chairs, these armchairs that look in a way like avocado. It takes a very high degree of intelligence to interpret what you're typing and to create an image that actually describes it. Here is another one, and this is I'm sure that there was never an example for it for the algorithm: a bench in the shape of Pikachu. And you can see how well it understands the concept of bench and the concept of being in the shape of something, in this case, Pikachu. There is another nice one. This is an illustration of an eggplant with a mustache playing a guitar. And these are examples that, of course, were never seen, but it was able to be creative enough in order to generate these instances of an eggplant playing guitar with a mustache. All right, so we're going to quickly review this timeline of the entire field of computer vision and of deep learning, and understand where we stand today. So our journey begins at the 1940s, and McCulloch and Pitts actually introduced this something that was supposed to imitate a neuron. It's not yet using machine learning, but it's the first try to make algorithms that are inspired by the human brain. It was actually very simple. And this is like maybe where the journey towards deep learning begins. So a big thing happened at 1957. The perceptron algorithm was introduced by Rosenblatt. Let me just say, I see from time to time, I see messages come up in the chat. So in case that these are questions, I'm not going to be able to fluently see them. So you can unmute yourself and ask a question if you want to. Okay. So
we will also, sorry. We will also try to answer on the chat.
Okay, great. So in 1957, we have the perceptron algorithm by Rosenblatt, and this time these are learned weights, and this is probably the first step towards a learned neural network, even though it's not a network, it's shallow network. And then something really disturbing happened at the late 1960s. Marvin Minsky published this book about learning, and one of the things he showed is that a problem called the XOR problem, which you probably understand the context of, cannot be solved using the perceptron algorithm. And this thing, among other industrial reasons, has lightened the an era that is called the first AI winter. So governments and companies didn't want to invest in artificial intelligence. All people practicing it had very little fundings, and it was quite a bad time. However, during this time, some other fields began to show up. And one of them is this intersection between understanding vision and the human vision. And in the 70s, there was this very famous and important book by David Marr, which is an important figure in computer vision today, and I mean, has influence on what we have today. And this book was especially important because, among other things, it advocated hierarchical representation of images in the human vision pipeline. And we also have our own relation to it, because you can see who was his PhD student at the time who helped doing this. So we had the representation there for the 70s. And 1980s, we have the first convolutional neural network, and we're going to learn in the third lesson, we're going to talk about convolutional neural networks, but this is the basics. This is the basis for most computer vision in deep learning that we're going to practice. And this is by Fukushima, and there is still not the famous backpropagation algorithm for optimizing the system, and it's mostly coming out of neuroscience, understanding the human vision and describing it using these hierarchical shift invariant filters But this is indeed the first convolutional neural network. At 86, Geoffrey Hinton, one of the godfathers of deep learning, people sometimes say, was able to use backpropagation for the first time. The actual backpropagation algorithm actually existed since the 60s, but he was the first to implement it inside a neural network. So this was a very important step into be able to train neural networks the way we do it today. And then there was another era of the second AI winter for various reasons. Again, investments in artificial intelligence went very low. However, during this time, people did important stuff. So this is the very young Yann LeCun, which is also very famous, demonstrating using CNN together with backpropagation and to be able to identify handwritten digits. And this was actually, this video is from the early 90s, but he worked on it already at 1989. And the new thing here is taking ideas of convolutional networks from Fukushima and to be able to optimize it using the backpropagation technique as Geoffrey Hinton inserted into deep learning. In 95, we have the finalized version of the support vector machine, the soft margin kernel SVM, which was very, very useful. And we have the network of Yann LeCun, the LeNet5 at 98. And then some things happen that are related to machine learning and computer vision. We have the SIFT algorithm, scale invariant. Please mute yourself, everyone who's not me. And we have the random forest algorithm at 2001, and this was actually used for the Kinect cameras, the famous Kinect cameras at that decade, and the famous Viola and Jones that were able to do face detection using boosting, actually add a boost, and spatially created filters. So all this era is actually can actually be described in my terminology as the neural winter. So it's certainly not an AI winter because really great things happen like the SVN, the random forest, etc. But due to these successes and due to the fact that the LeNet5 of Yann LeCun was only able to identify handwritten digits and nothing else, it wasn't good for images. It just couldn't work for large RGB images. So no one wanted to practice the study of artificial neural networks. And then happened one very important thing. The big thing was at 2012. So Alex Krichevsky was a student of Geoffrey Hinton, and he was able to do this network called AlexNet, which by far won the image recognition challenges and had very impressive results. One key difference that made it do so was the fact that they started using, instead of using CPU, like everyone was doing, they were using their GPU, their graphical processing unit, in order to activate this neural network, so it could be much faster, and then it was feasible to train it on large amounts of data with large amounts of parameters and to get fantastic results. And this is where the revolution started, and probably the reason you're now in this class is actually has a lot to do with this point in time at 2012. So we have this resolution, and the chart you're seeing here is not COVID. If the Google Trends of deep learning, and starting from 2012, it just boomed up. And during this time, with important inventions, I will name just a few of them. So in 2014, Ian Goodfellow proposes, together with Yoshua Bengio, proposes the GANs generative adversarial networks and amazing generative model. 2015, Kei-Ming He comes up with the ResNet, which cancels the limit over the depth of neural networks, and people are now able to do very, very deep, huge networks using this trick. And 2017, Ashish Vaswani and many other guys at Google Brain introduced the transformer, which is a module that is based on a thing called self-attention, and it was a key contribution to many natural language advancements that followed until today, that we have really super amazing things done using algorithms based on it. So the guys who fought for deep learning during all this time finally got the recognition. I mean, they got the recognition much before, shortly after 2012. But in 2018, Yoshua Bengio, Jeff Hinton, and Jan LeCun were awarded the Turing Award. And this kind of symbolizes the understanding of the community that deep learning is one of the most important advancements in technology altogether. Okay, so today we're mostly going to discuss supervised learning. So we're going to discuss several classical aspects in supervised learning, and we're going to build this in a way that is going to prepare us for our next meeting, in which we're going to familiarize ourselves with neural networks. So let's see this very simple example here, and say that I want to do the classical challenge of spam detection. So I'm getting many emails, and I want to be able to classify them. This is called classification. So each email I get has these as many properties, like the number of new recipients, or the email length, or the country it came from, and also it has and also I know as a human being who checked it later whether this was a spam email or was it ham. Sometimes people refer to something that is not spam as ham. I think it originates in the US Army. So for terminology, we're going to call every line in this data is going to be called an instance. These are the instances, and each such instance has its own features, and we're going to match each instance with a label. And there are many types of features. So you can see the first two features are numeric features, but we have also categorical features. They can be also divided sometimes to nominal and ordinal. And most today, especially, and also most of this course, we're going to discuss numeric features. So let's not look at these categorical features for a while and understand what we see here. So we're able to look at every instance as if it's a vector in this subspace. So for example, we can take all the emails we have, and we can localize them in this subspace. And you see the x-axis is new recipients, and the y-axis is the email length. And we use color coding. So red means spam and blue means ham. And our goal in supervised learning is use this data to be able to find this rule saying, when I get a new one, when I get a new email, is it going to be spam or ham? And we call this thing a hypothesis. So my hypothesis could be, for example, that I'm drawing this line, and everything below this line is spam, and everything above this line is ham. And when I get, now if I get this new test instance, I will be able to classify it using my hypothesis, and of course it's going to be spam because it's on this side. So let's do it just a tiny bit more formal. Oh, sorry, one thing before. We differentiate between two challenges in the world of supervised learning. So the first one, the first challenge is called regression. And here, this is the challenge of finding some continuous and some continuous labels. So for example, if you want to predict house prices, okay, and the other one is classification, where you can have not several, but you have a finite number of classes, and you want to be able to classify each instance you get to one of them. So classification is discrete and regression is continuous. And for example, let's take it to the world of computer vision. So for regression, one example we can look at is called image denoising. So we get a noisy image and we want to be able to generate new pixels that are now clean. So the values are continuous. So this is a regression. And another thing we can look at is this challenge of localization. So think about it. I want to find where the stop sign is. So for example, I can describe it using X and Y coordinates of the top left corner that I need, and the height and width of this bounding box. For classification, so it's a very familiar challenge, the image classification. So in this example, you can see classifications of cats and dogs, but there are famous competitions with for example, with the 1,000 classes. Okay, so let's do it a little bit more formal. So in supervised learning, you can look at this diagram here I took from Andrew Ng. So we have our learning algorithm, and our goal is to produce this hypothesis that we will be later able to apply to some X, to some test example, and to get our predicted label, our output, what we believe should match this X. So you can say that the learning algorithm is applied to the training set, and the result would be our hypothesis. So the training set, okay, sorry. So here you can see this, and the training set consists, as we've seen before, of inputs and labels. So we can say that each row, we call it an instance, and each instance has its own label. And if all the features we're using are numeric, then we can formulate this as matrices. So we have the X matrices, and the lines are, the rows are instances, and the columns are features. As for the labels, so the labels can actually be vectors. In classification, we usually use one-hot vectors. And they can also be vectors for regression. For most of our discussion today, the labels are going to be scalars. So this is not going to be a matrix, but it's going to be a vector. And so this is our training set, and this is what our algorithm gets. And there are three things that make a supervised learning algorithm. The first one is hypothesis class. So we need to predetermine which are the hypotheses that we can choose from. So one example that we're going to actually discuss today is the linear case. So I can say that my hypothesis class is an infinite class of all linear mappings. And so it will be very common that we're going to describe this class not as you see here as a list, but as a parameterized function. So for example, all possible linear, all possible polynomials to a certain degree, etc. And whatever hypothesis we have here, each hypothesis should be a function that takes us from the world of X's to the world of Y's. So from the world of the inputs to the world of labels. The second thing every supervised learning algorithm has is a defined loss function. The loss is sort of the metric that we're using. The loss determines what makes a good approximation when looking at the label and the predicted output that we get. And finally is the optimization method. So this is the way, the optimization method is the way that we search through the hypothesis class to find the hypothesis that minimizes the loss. So if you have this to describe a supervised learning algorithm just in one sentence, so it includes an optimization method that searches inside a hypothesis class for the hypothesis that minimizes the defined loss. Okay, so you've been very quiet. Maybe you were asking many questions in the chat. I don't know. Are we good? Are we cool? Everybody Okay. Great. So the first method we're going to talk about is called linear regression, and probably some of you bumped into it before. I have this feeling, and what we want to do is we want to fit a linear mapping to our data. So given inputs and labels, we want to find this is for, of course, for regression or for classification. We want to be able to best predict this matching. And as you can see here, usually it's not going to be perfect. Let me just point out that this is the one-dimensional case, and we're going to look at one-dimensional cases because it's the easiest for us to show. But practically, it's going to be usually many dimensions, and then it's not going to be this line as you see here. It's going to be a subspace or a hyperplane. Okay. So we need to define, if we're now defining a new supervised learning method, so we need to define these the three elements it consists of. So the first one is the hypothesis class, and I guess you understand by now that the hypothesis class of linear regression would be the linear class. So let me just use annotation. I just have to grant myself annotation rights. Okay, so okay. All right, so okay, we'll do it in a minute. Okay, so we'll do it from here. So as you can see, I can describe the hypothesis class in this using parameters. So I'm going to define this parameters vector theta, and I'm going to say that my hypothesis class consists of h sub theta, where theta is a vector in R to the n. And now I'm going to define how each hypothesis looks like. So this is what it looks like. Sorry for this. So this is what it looks like. So we have this linear mapping. So you see we have this bias and this linear combination of the inputs. So given some instance x, we apply this linear mapping, and or you can look at it vectorized. So we have this bias scalar plus a vector that we get standard inner product with our vector x, and the tilde here is because this vector theta is different from this one because it doesn't include this the bias here. However, we can do this nice trick. So for those of you who don't like too many parameters, so one thing that we can do is we can define our input a bit differently. So each vector we just add 1 at the beginning of the vector, and then we can simply just multiply. Say that our hypothesis is multiplying the vector theta with this vector, and you can check and see that it works well. It's just the same as this one. So this is a nice trick, and we're going to discuss linear regression most of the time this way. So just multiplying by this vector of parameters. So we defined the hypothesis class. We need to define also the loss, and the loss is going to be the very famous mean squared error. So we're going to take the mean over all the instances. This is what you see here, and then we're going to take the difference between our prediction to the true label, and we're going to take the square of it. And again, this can be looked at vectorized. So if you think about the matrix capital X that we've seen before. This is where all the rows are the instances. So now actually you can just take the spectral norm of X multiplied by the vector theta minus the label vector Y. This is the vector of all labels, which we said that are now scalars. They are not all for each instance we have a scalar label, so we have a vector of labels. The size of this vector is M. M is the number of instances we have, whereas N is the number of dimensions we have in our problem, the number of features we have. Okay, so all these vectors here are in the size of M, so this is a valid reduction. Okay, and this is the way we can describe our loss. Lastly, we need an optimization method. So for the optimization method, we will cover two approaches. One is called normal equations, and the other, and we're going to discuss it just now, and the other is called gradient descent. One is very impressively does this like in one stroke. You just apply this analytical solution, and you get your minimum loss theta just by one step. And the other is an iterative method, and we're going to discuss this. So let's talk about the normal equations. So remember that what we're looking for is to find the best theta, the best vector that brings to minimum this loss that we have, this mean squared error. Okay, so let me just. I want to see you from time to time. Am I clear? Is everything okay? Are we good? Okay.
Yes.
Okay. So this is what we're looking for, and we're just going to talk about the intuition of normal equations. So let's say we have this label of vectors y. This is what we want to do. The ideal thing that could have happened is that we could predict this vector exactly. Unfortunately, this is usually not going to happen. As you've seen, usually a single linear function can't fit all our data. We're limited. So looking at it algebraically, the way we're limited is that our solution has to be at the span of the rows of the matrix X. Okay, so whatever solution we're going to have is actually buried in this span over here. Now the intuition is that we're going to be looking for the best possible solution, the closest solution that we can. But the geometric intuition actually suggests, when you think about the distance of some point from a subspace, we know that what we actually want is that the difference between them, what we define as the error vector, is going to be perpendicular to this subspace. So in algebraic terms, it's going to be orthogonal. We want the error vector, this x theta minus y, to be exactly orthogonal to the subspace, and this means we will have the minimum solution. This is not a proof what I'm doing here. This is an intuition. Okay. So one way of saying this is that every vector x that is in the span of the rows of the matrix X, okay, every vector x, we want it to be orthogonal to this error vector E. In particular, it means that that specifically the rows of X, we want them to be orthogonal to the error vector. So we can use a standard inner product to describe it, and for each, and this is the zero vector over here, for each row of X, we want it to be orthogonal. So this means that we should get a vector of zeros when doing this multiplication, when applying the matrix X to the error vector. And from here, it's very easy just to rearrange everything. And if X transpose X is an invertible matrix, we are now able to describe the best solution, our predicted solution theta, just as a closed form very easily, just as a closed form multiplying these matrices, and we get our solution. This is called normal equations. And let me just say that the formal proof for this you're going to do in your homework. This was just an intuition. You're going to have to use differentiation. And also in the homework, you're going to discuss what are the terms for X transpose X to be invertible and to make this solution possible. Okay, is everything cool? Are we okay? Okay, so please, if you have questions, feel free to ask them. I'm used to, people usually interrupt me more than what I'm witnessing today.
I have a question, maybe it's stupid, but
Sure.
with that X and Y, you have theta, right?
Sorry, again?
With your X and Y, you find theta, right?
You're asking if I'm applying theta? What?
You use X and Y and you find the theta that minimize, sure. Right?
Yeah.
But maybe with another XY, the theta will be different, no?
Yeah, so please note that X and Y are the matrices. This is all the data I have. So it's not just a single instance X. Okay, it's the matrix X with all the data, the training data that I have. Okay?
Yes.
Great. Okay.
So if you have a training data, then you get a parameter, so you use it and you don't say that maybe it could be another parameter.
So you're saying, let's say I have a certain amount of data and then I find theta, but say that I had different, or maybe I'll just get more data, then theta can change, right? Is this what you're referring to? Yeah, yes. So this is truly a problem that we're going to discuss in a while. But let's just assume for a while that the data you have represents the data you're going to be tested on. So yes, it's true that if you like re-sample your training data, you may get things that are a bit different. But it's usually safe to assume that they're close enough. I'll say some things about it in a while when we're going to talk about the decomposition of the error. Okay? Yeah.
You just do this one time and then you find the theta. It's not like a process.
No, it's not a process at all. You just do it once. It's a closed form and you get your theta. Yeah. However, let me ask you this. Will normal equations always be practical? So we've seen, yeah, it's true, they work. But what do you think can make it not practical?
Huge data. If we have huge data, we cannot apply it to a computer.
Great. So I think great. So I think I heard most of the answers. So the answer is no. Usually it will actually not be practical. Okay, so one reason is that X transpose X may cost unreasonable memory. If you have a huge amount of data, then now this is not a practical thing to do. You can't actually do this thing. And then you also have to do to invert it. And the second thing is that in some cases, it's not going to be applicable at all. So for example, if you use a regularization term, thing we'll talk about in a few classes, or if you're using, let's say I don't want to use MSE, I want to use different laws, or what we're actually aiming for next, if we have more layers, so this closed form solution doesn't hold, okay? So I will have to find other ways. So.
Can you explain again the second?
Yeah, so there are some modifications that I might want to do to the setup, and then the normal equations will not hold. For example, if I use a different loss, if I'm not using this squared loss but something else, so all the derivation we just did it will just not be correct anymore. Or if I add more layers, so it's not just a linear hypothesis now, but something more complicated. Again, the derivation we just did, unapplicable. Okay. So the normal equations is a great solution when you have relatively not too much data, and when you have this very specific set of restrictions that normal equations is applicable for. Okay.
Can I ask a question?
Yeah, sure.
About one, x transpose x is should be n by n, right? Like where n is the dimension. So it's not the x depends on m, the number of instances, but x transpose x shouldn't be, right?
So x transpose x is the size of the number of features over the number of features.
Yeah.
But to achieve x transpose x, you need to do a multiplication of m by n matrix with n by m matrix, and this will be costly. If you don't have a lot of data, it's possible that you don't have a lot of data, but for example, you have a lot of features, in which case x transpose x will be a cheap thing to do, but then inverting it will be very expensive.
Yeah, but usually we have like a lot of data and less features.
It's the classical case, yeah.
Yeah, and so it will be costly, more computations than memory, right?
Yeah, I agree. You mean not memory, but time.
Yeah.
Right. Yeah.
But also, it's not really expensive, even it's a lot of data, right?
No, it depends what is a lot. I mean, you can have millions. You can have.
All right.
Yeah.
All right. Never mind. Thank you.
All right. So okay. So what I'm suggesting that we'll do now is that we'll have a short break, a 7 minutes break, and we're going to continue just at 20 minutes past 10. Okay, is that okay? Okay, so let's do this short break and we'll meet in a while. All right, so if everyone can turn on their cameras, I'll see that you're here and we'll continue. So in case it wasn't mentioned, it's quite important for you to have your cameras on, at least for us as lecturers. It's very important. It's easy for us to interact and to see your faces, do like this sometimes, and it gives us feedback. Okay, so I'm really asking from everyone to turn your camera on. And by the way, you will not, the recordings will include only a video of the lectures, and they will have your audio if you ask questions, but they're not going to show your video even if you ask a question. Okay. So
can I ask a question?
Yeah, sure.
Can you go 2 slides before the previous 2 slides?
This one?
Yes. The formula that you show, x transpose multiplied by x theta minus y equals 0.
Okay.
Shouldn't it be x transpose theta multiplied by x theta minus y? because it's a point in the plane?
No, okay, yeah, I'll clarify this. So x theta, okay, is the point in the plane, and you subtract y from it to get this vector over here.
Mm-hmm.
And we want this vector to be orthogonal to every vector in this subspace. And in particular, all the rows, sorry, of the matrix X. So this is the zero vector. You get this, whatever vector of X, of the matrix X you take, you get the scalar 0. So if you take the entire matrix, you get a vector of zeros.
You want it to be perpendicular to the plane and not to the specific
I want this to be
x theta.
Yeah, exactly. I want the error vector, this one, to be orthogonal to the subspace, which means it's orthogonal to each and every vector that exists in this subspace.
Okay, thanks.
Okay, great. So, where were we? So we're just saying that normal equations are not always applicable. So we'll discuss a different solution now. And a different solution would be doing this iteratively. So how about if we iteratively reduce the loss? So let's say you're at some place, and this is me about 10 years ago near the highest village in the world, in India. And let's say that I want to just go down, okay? So one thing you can just think about is, why don't I do it just step by step? Wherever I am, even if it's dark, even if I don't know where the bottom is, I'll just take a small step from wherever I'm standing. I'll just, I'll fill with my legs the steepest descent that I can find, and then I'll go this way. And after I do this, I do it again and again and again and again. And this way, I'll be able to gradually reduce the loss. So here is a question for you. Will this guarantee for me to be getting to the global minimum?
Local minimum.
Yeah, so this is correct. This only guarantees, and not even that, that I'm going to get to a local minimum. And I can only say something about a global minimum, in which case, what would be the condition for which I can say that I'll probably get to a global minimum. Any ideas?
Convexity.
Exactly. So if my loss function is convex, I'll probably get there. I'm saying probably all the time because we have this step size that I'm doing also, that is also a factor. Okay. So are you seeing this as an animation, or are you seeing this frozen?
Frozen.
Frozen.
Oh man. Okay. Now you see it as an animation, right?
Yes. Yes.
Okay, great. So what you're seeing is the two spaces, and on the left you can see what we call the parameter space or weight space. And it's important for me to show it this way, because when we practice optimization, then we're saying that our training set is actually frozen. We're not doing anything that is data related. We're taking the entire training set as it is, and this is sort of frozen in the loss function, which we look at as a function of the weights. So what you see on the left is a function of theta 0 and theta sub 1, okay? And on the right, you can see how this translates to the data space. So when the loss gets lower at the left animation, you can see that the linear fitting is actually closer to all these vectors in space. Okay, is that clear? You understand this differentiation? Are we cool?
I didn't get the idea. Can you explain it again?
Sure. So when we do optimization, okay, so we look at our data as frozen. The data is not changing. Sometimes people think that something is changing about the data in the process. But we take the entire training set now, okay, and and this sort of determines the shape of our function, but the variables that we're changing in the animation on the left are the weights, are theta. In this case, we have only two of them, theta sub 0 and theta sub 1. These are the only values that are changing, while S, the training set, is actually a part of the shape of the function, the description of the function. And on the right, you can see how it translates for a linear mapping. So this is in the data space. So you have the x-axis and the y-axis. Y is the labels and x is the instances, and we can do this fitting. This is how the hypothesis looks like. Okay, so I'm going to do a very quick calculus reminder so that we understand why we're going to use this gradient. So I'm going to remind, I'm sure everyone has seen this before, so we'll do it quickly. So I'm going to remind about directional derivative. So let's say you're at some point and you ask, how hard for me is it going to be to walk to a certain direction, to a certain vector direction? So this can be asked as, what if I take this cut of this many dimensional function? I just take this one dimensional cut, and I'm going to ask, what is the derivative at the point I'm in for this cut? And this is called the directional derivative, and it can formally be presented just as many of you are used to see the definition of 1D derivative, only that you multiply this epsilon here, you need to multiply it by the vector you go to, and to keep it just the direction, you divide by the norm. And you can prove that if this function is differentiable, that you can actually, this expression can actually be written as this multiplication of all the derivatives to all the in all the dimensions of the problem. So for x1, for x2, etc., each one multiplied by the size of the element of the vector to this dimension. This is what we get here. This is something you can easily prove, but it has to be, the function has to be differentiable. And I'm sure that you see that the structure we get over here is actually the structure of an inner product. Okay, this is just the definition of an inner product between one vector would be the vector v, and the other would be this list of derivatives. And I'm sure that most of you, and maybe all of you, know that this vector here is known as the gradient of the function f. So this is the, so for a multivariable function, we have this vector field, which is the gradient, and at every point is the, it gives us n derivatives, one derivative for each dimension of the function f. So we can actually write it this way. And for those of you recognizing geometric interpretation of the algebra, you can state now that a directional derivative is the projection of the gradient over the direction vector. So we just multiply the gradient with the direction we want to go to, and this is going to be the steepness that we see here. And this is important because now we can take advantage of the Cauchy-Schwarz inequality and argue that the maximal value that this expression can actually get to is the norm of the gradient of f. This is the maximal value this expression can be, and this is obtained when v is exactly parallel to the gradient of f. So putting it in simpler words, the gradient always directs us to the steepest ascent, okay, the steepest direction we can go to, and the side of the gradient is this maximal steepness. So in our case, the gradient is probably going to look somewhat in the direction of this arrow, but the gradient can be defined to every point in space. So this is a vector field, so every point has its gradient. Let me ask you a simple question. So we've seen the gradient takes us up, but usually with loss, we want to go down. So any ideas, any very, very simple idea, what we can look at that can actually take us to the bottom and not to the top?
Subtract the minus.
Yeah, so everybody, I guess, is aware of it, that we can just take the minus of the gradient, and then at every point, we're just going to always go down as far as we can towards the local minimum. So what is gradient descent? From here, everything is super simple. So if we take the gradient of the loss, we have the loss, which is a function of theta 0, theta 1 until theta n. And so this is how it looks like. And remember that we want to just go down by steps. So the gradient descent algorithm is attributed to Cauchy, to Augustin Louis Cauchy. And it's a very, very simple algorithm that works like this. First, you initialize all your weights, all your parameters, you initialize them to be random. And then what you're going to do at each step, this is an iterative algorithm. At each step, you're going to update. Please note that this is not an equality sign, but an assignment sign. Okay, we assign as our new set of weights data the old one, but with the gradient subtracted from it, and the gradient is multiplied by this alpha over here. So alpha is called the learning rate. The learning rate is sort of the step size that we take here, or a factor of the space, a factor of the step size that we're taking, and this is a hyperparameter. And the difference between a hyperparameter and a parameter is that parameter is something that we need to learn, is that our optimization algorithm changes and we're finding the best one. And the hyperparameter is an entity that the user, the programmer, the developer, whatever, has to predetermine. Okay, hyperparameters are designed by humans. So this would be, I'm saying this sort of the step size or factor of the step size, because the step size is also influenced by the size of the gradient. So remember, the steepest, the steeper you get, the gradient is going to have a larger norm. So the two things influence what is the size of the step you're going to do. The norm of the gradient, how steep the place you are in. For example, here it's going to be bigger, but when you're in a plateau, it's going to be smaller. And the learning rate. So what we are familiar with by now is called full batch gradient descent. So, and
happy birthday to me.
Okay. Happy birthday, but please mute. Okay. So this is called full batch gradient descent, what we've just learned by now. And the really big problem can be found here. At every single step that we do, we have to run this calculation over the whole data. So let's say we have 1 million instances of data, and we take this gradient. We have here these 1 million parameters of this loss function, and we have to do and you know, think about a mean squared error loss. So the mean squared error loss needs to take an average of over all the data that we have, all the training set, right? And this means that a single step, not all the steps, just a single step is so expensive that we usually can't afford it. We can't do it. One single step will take us forever. Okay, so this is a problem. And one way to solve it is called stochastic gradient descent, SGD. And stochastic gradient descent says that let's do a very simple thing and much, much less expensive. Instead of taking the whole data that we have, at every iteration, we just, by random, just choose one instance from this data, one pair of X and Y. And we're going to do everything just according to it. So if this is an MSE loss, it's not going to average anything, just going to take one of them. Okay? And you can actually show that by expectation, the expectation of this process is the same as where the full batch gradient descent is going to take you, but the variance is going to be obviously bigger. But think about it, that if you do many steps, then eventually you average this variance over many steps, and by expectation you get to where you need, and practically you probably do something that is reasonable. Actually, this is a reasonable way to go. However, the variance is very, very big for each step. It can be messy. And there exists the golden path. And the golden path is called stochastic mini batch gradient descent. Okay? This is like the full name. Sometimes when people speak, they usually say, I work with batches. Okay? And the stochastic mini batch gradient descent says, okay, let's just take something here in the middle. So no, I'm not going to take just one instance at each step, and I'm not going to take the entire training set at each step. I'm going to take this batch, and the batch could be at any number that seems reasonable. People do something like 64, 256, whatever instances at each time. And this is much better from just normal stochastic gradient descent, because each step has much lower variance, and the trade-off is an unfair trade-off. So it's actually much better. So what you gain from having just a few more examples for each step is much more, is much better for you than what you lose on the calculation. So we can look at this diagram over here. It's not a true one. It's someone painted it. I took it from some blog. And you can see that in blue, you have the full batch gradient descent. So it's very directed. You're going to hit just what you need, and you're always going to go down the hill. However, each step you see here, each blue arrow that you see here takes forever. If you have a million instances, then you have to do these million calculations to do for each step. On the other hand, you have this stochastic gradient descent here in purple, and you see that it is very messy, and you're going to need many steps in order to converge. And sometimes, if you have a very non-convex function, it can be risky. You can find yourself, going over here, or finding yourself in a bad local minimum at someplace else. And you can see in green the mini batch gradient descent. So you have this bit of a variance, but it's much more directed towards the point than the purple one. It's obviously the best choice. Now, in this choice, you have to choose the size of the batch, and this has many considerations like the memory you have, etc. Okay, but this is what people usually do. This is the best way to do it, and this is what we do for training neural networks also. So let's project this gradient descent into our linear regression method. So this is what our loss looks like when it's split open. So you see the hypothesis is right here, okay, applied to the x's, xij from our matrix. This is the label y, and we have double summation, one for the hypothesis and another summation over all the instances. I'm using now a small m, saying this is the size of the mini batch that I'm using. And now what I want to do is just find the gradient. And to do so you can do this calculation like in vector calculus, but I wanted to spread it open the easiest possible. So what we're going to ask ourselves now is what if I take the derivative of the loss with respect to some weight theta sub j sub 0. So it's a very specific, and without loss of generality, I'm going to take the derivative with respect to some specific weight in the vector theta. Okay, and the process is very simple. There's nothing, just simple derivation here. Just note that this summation can be cancelled once you do for specific theta j sub 0. Okay, and if we take what we have here, we can put this thing vectorize it. So what we have here, let me just explain this. So this thing is a column of the matrix X. So I annotated it this way. Okay, it's a column of the matrix capital X that matches the feature j sub 0. Okay, this is what you get, because if you look at this expression over here, so this is a product between an inner product between two vectors, right? So the vector that we multiply by is a column of the matrix X. And look at what we have here. We've seen this thing before. This is the error vector, right? This is x theta minus y. This is exactly what we defined when we worked on the normal equations. We call this the error vector. And this gives us a very, very simple formula for the gradient for linear regression. All you have to do is to, at each step, is to reduce from your vector of weights. You just need to reduce alpha divided by the batch size, the learning rate divided by the edge size, but by the batch size multiplied by the matrix capital X, which now has this different meaning, because if you just take a mini batch, this X matrix is not so large as the whole training data, right? It's just in the size of your mini batch. So it's small m by n multiplied by this error vector, which is in order m, and you just need to repeat this until you get convergence. And now I have a question for you. So my question is, can you find a relation between the convergence of this gradient descent and what we've seen before with the normal equations? So can you just find this curious of how these two are related? Say that I want the gradient descent to converge. Any ideas here?
If theta equals the extra part of x transpose x minus 1, no?
X transpose x minus 1. So what you're saying may be right, but I'm pointing out something a bit simpler. What I'm saying,
the error will be 0 when you substitute x with.
I don't think the error will be 0. It will be minimal, but not 0. What is going to be 0? Let me just. You were pointing out maybe this error vector will be 0. It usually wouldn't be 0, but what is going to happen is it's going to be orthogonal to the rows of the matrix X, and then I'm not going to update anything anymore because all this expression is going to be 0. This is theoretically speaking, if I'm able to get to this point. What I'm showing is that if by gradient descent I get to the point where I described by normal equations, then this will be convergence and I'm going to stop. I'm not guaranteeing that I am going to get there. It depends on the data and the surface and the convexity. Okay, are we good by now?
Assaf, should it be X transpose?
Where?
Here, the equation. If E is X transpose minus Y.
If E is X transpose minus 1, minus Y, yeah. So
then you should multiply by X transpose.
Because E is in the size of M and X is M by, yeah, I think you're right. Yeah, sorry for that. Yeah, it looks right.
Then it looks like the normal equations now.
Yeah, sorry, right. There should be transpose here. Yeah, thanks, man. Right. Okay. So let me clear this out of the way. Okay. So the next thing I want to discuss is the feature transform. So one thing you can do if, for example, you want to do classification, linear classification, but your data is highly non-linear separable. One thing you can do is transform your features. So what if I do this? The transformation here is taking this z-axis to be the square root of the radius. Okay, and now the data looks like this. And over this data, I can now do this separating line. And so it appears that if I transform my data, I can find a linear hypothesis that is able to now be a good hypothesis for it. And it's interesting also to see that I can project this hypothesis back to the space I came from. Sometimes I can, not always. And now I get this circular separation here. So whatever is a straight line in this mapping becomes a circle in this mapping. And maybe some of you, I don't know, we have some physicists here. see that this is in the world of general relativity is very similar to when you have in the presence of mass, you have the Schwarzschild metric, the Schwarzschild metric, and then geodesic lines that are supposed to be straight within this metric. To an outside viewer, they are going to be, for example, circular or any other possible shape. I should also mention that usually we want to add more and more features, so it can be beneficial to take, for example, this 2D description of features and add a third dimension, and now we have this more dimensions than what we had before. And we're able to do this linear separation. And for those of you familiar with the kernel trick, for example, for support vector machines, know that you can actually do this for infinitely many features. You can transform finite features to have to a space with infinitely many features, and this can be very beneficial. So this is very exciting because what you can do now, you have your input, and you first you can do this feature transform, and then you input what the transformed features into a linear hypothesis. And this means that implicitly, what you have now is a non-linear hypothesis, even though everything that has something to do with your learning mechanism is linear. You can use here linear regression. And one very nice example for this would be using the feature transform for polynomial fitting. So how about if the feature transform would be like this? Let's say our input is just a single dimensional vector. Okay, it's a scalar, right? So just have this scalar x. And now my features in this feature transform are going to be, so x sub 0 is going to be 1, and x1 is going to be just the x that I already have, and x sub 2 is going to be x squared, etc., to some degree of the polynomial that I want, p. Okay? And now this is very cool because I can do polynomial fitting using just linear regression. So I'm not doing anything complicated about searching through polynomials and the hypothesis that I know nothing about. Okay, all I'm doing is linear regression with p dimensions, p+1 dimensions. All right. We need to analyze now what the error is made of. So think about it. If we have the loss of what we finally get at the test, we're done training, we do the test, we get some loss. And we need to ask ourselves what prevents us from having loss of, let's say, 0. And I'm putting the 0 in quotation marks because you can define loss types where the minimum is not 0, but something else. So I'm putting this in quotation marks, I mean the minimum possible loss. And we're going to split it now and to see what the error is made of. So let's see all this gap, what it's made of. So 0 loss theoretically could be achieved if my data was clean and I knew everything about it and I wasn't limited in any way. However, the true data usually will have noise. So there is no deterministic relation between x and y. There is some statistic relation. So x is just a statistic restriction. You get y given x, but it's not direct mapping. This is the case in most cases. This is like this. So in this case, it will look like this, and we call this a base optimal predictor. Okay, this is like a theoretical predictor, which is the best one that you can have, but it's still not this quotation marks 0 loss. Now you have to remember that we only work with our hypothesis class. So whatever we have is inside the hypothesis class, right? So now we can look at another gap that we have. So say that we have say that we have to choose only from the hypothesis class. So we have H star. This is the best in the hypothesis class, but the hypothesis class is not perfect. So for example, we were looking before at linear hypothesis class, at the linear hypothesis class, and you can see that this sort of data that you can see here, this sort of data, we cannot fit it using a linear function. Okay, so this gap is called underfitting. Okay, this simply means that our hypothesis class is not complex enough, is not complicated enough to be able to describe the data that we have. Next, what we have is the gap between the best hypothesis in our class and to the best hypothesis in the training set. And you have to remember that whatever you do in the training set is fine. But now you have to think about generalization. Generalization is to be able to determine, to have output over the test from things that you learned from your trained data. And you can have here this gap, and this is a very famous gap. It's called overfitting. And this means that, yeah, sure, maybe your hypothesis class is a very good one. And you can see that in orange, you can see the training instances, and in blue, you can see many test instances. And you can see that I'm perfectly able to match to my training set. However, this is very far from the test set. And this is called overfitting. You do well on your training set, but you do very bad in the test set, okay? And on top of all of these things, what you finally get is even worse because there is the optimization gap. So for example, you do this optimization process and not necessarily you're even going to get this H that is best in the training set. HERM is called empirical risk minimization. And it's not sure that you're going to get this one. For example, if you use gradient descent and you use, let's say, a step size, a learning rate that is too big, then you might not be able to reach to the bottom here. Okay, are we fine by now?
Can you only explain the first gap between the 0 and the best possible H?
Yes. Okay. So say that you want to predict. I can tell you certain features. Like today was rainy. Okay, and there is a car with a certain type, and now you have to predict, to do classification, whether or not there is going to be a car accident. So I'm sure you agree with me that there is no like true mapping. There is no ground truth here. There is some kind of probability that is that relates X and Y, but there is no direct deterministic connection between X to Y. So in this case, even the best predictor possible in the world can't have this zero loss. It won't always be right. It will just do the best guesses, like with respect to the statistics. Okay. So this brings us to a thing called the bias variance rate. Yeah.
Can you go back, please, 2 slides?
No, sorry. We're kind of running out of time, and I have to keep on. I will stay when we're finished. I will stay and answer more questions. Okay. Sorry for that. So this brings us to the very famous gap of underfitting and overfitting, and this is influenced by several things, but the most apparent thing is the model complexity. So if we have a lot of parameters, we can do a very, very good fitting, then we're at the risk of doing overfitting. At overfitting, you're going to see the training error very low, but you're going to see the test error very, very high because you get lied to by your own ability to predict upon your training set due to things that are only apparent in the training set. We're going to see example in a minute. And the other side, you have the underfitting. Underfitting means that simply your hypothesis class is not complex enough. The data is very complex. For example, you wouldn't expect to be able to do a classification of large images of cats and dogs using a linear classifier. Life is not that simple, right? So if you have high training error and high test error, you're probably overfitting. Maybe you have optimization error. And if you're the other side, if you have test error that is high and the training error that is low, then you're probably overfitting. And there are many philosophical ways to look at overfitting, but it's also influenced by data. So if I tell you, go to sleep for half an hour, and then I can fix you a bed that will always be good for you. So you understand that this is overfitting that was led by poor data. Okay, we only had very little data, and you can understand now that a lot of data means that you will be able to use a complex hypothesis class and still be able to get good results. So for those of you who know, we're not going to discuss it, but in machine learning, supervised learning theory, you have the fundamental theorem of statistical learning stating actually numeric connection between the data, the complexity of your, it's called the VC dimension, the complexity of your hypothesis class, and can give some guarantees on what you're going to get for the simple case of binary classification. Another nice example is if I show you this data. So I have this matrix here. This is the X, and I only have one single instance of data, and I show you the Y, which looks like this. All right. So the true hypothesis is to take the matrix and to take the square of the matrix. Okay. But what you may think is that you take the digits and you use them again, so you can see how data can influence this. And let us finish by this polynomial fitting example that I made for you. So I'm going to show polynomials of different degrees, and then what we're going to do, we're going to learn from it both how this polynomial fitting works, but also we're going to have a very good example for underfitting and overfitting. So okay, so let's say I have this deterministic data at first. Okay, this is a third degree polynomial, but to make it more realistic, I add some noise to it. So this is the test data that I have. Okay, this is how it looks like. Okay, are we good? Everybody can hear me well? Are we doing great?
All good.
Great. So now I'm going to have my training data. The training data is sampled from the same place where the test data came from, and I get this several, you see, training points. And now this is going from one dimension. This is a one-dimension mapping, and I want to match this the best I can. Now let's go one by one over the degrees of the polynomials that we have. So 0-degree polynomial looks like this. It's actually just taking the mean of all the training data that I have, and you can see the test error is pretty large, and the train error is 2.1, whatever. On the left, you can see a logarithmic graph describing the test error and the train error. Train will always be orange, test will be blue. Okay, so this is what we get at this point. Now we're going to a degree of 1. This is just linear regression, okay? And you can see that things got improved. We get a better test error, better train error. Let's go on. 2 is slightly better. It just curved a little bit. Now we have 3. Sorry?
What is the train error?
Both are MSE losses. Okay?
Oh, okay.
Everything is measured in linear regression. We measure by MSE. All right. So a third-degree polynomial gives us this test error, which is probably nice, and this train error 0.29. And you see that everything looks good. If I go to a degree of 4, it also looks about the same, not bad. Now something happens. As I go to 5 and 6 and 7, things get crazier. Okay, so look at the train error. The train error is lower than what we had before. You see, it got lower, but the test error got somewhat huge. Okay, and you can see that the more I go on and on, I can actually fit my training data very well. I can fit it so well to the point where my train error is practically 0. Okay, it's like my train error is practically 10 to the -7 or so. Okay, but the test error is now unbelievably huge. Okay, this is a logarithmic scale here. Okay, and the reason for it is that I'm using a hypothesis class that is more and more complex and is able to do a very, very good fitting, which is too good, which is overfitting. And I can't find a simple rule to describe my data so that it will be able to generalize and go on and on. Okay, so if you look at this plot we have on the left, you understand that if you look at around the degree of 3 and to the left of it, so this is the underfitting area. Okay, and most of what we see to the right of this degree of 3 is the overfitting area. Okay, and this sort of makes sense because if you remember, we started from data that was sampled from a third-degree polynomial. Okay, So, so it makes sense that the measure of complexity of the rule describing the data is going to be somewhere around a third-degree polynomial. So we're mostly done here. I just want to say that in this week's tutorial, in Thursday, so Niv is going to tell you about linear classification. And next week, unfortunately, you're going to meet me again, and we're going to discuss neural networks and backpropagation. So if you have more questions, I can stay for several more minutes. I know that someone asked something and I wasn't able to answer at the time. So I'm going to stay for a few more minutes. So that you can ask. Okay, I want to thank everybody. Thank you for listening and welcome to our course. Please remember that we have our homework number 1 in the Piazza. It is due in about 2 weeks. Okay, and thank you for listening, and see you again on Thursday. Bye bye.
Thank you. Thank you.
Thank you.
Bye bye.
Thank you.
Thanks.
Thank you. Bye.